In this session, we will discuss computation of deflections of beams using the double integration method. Now, this is a method which is typically covered in a mechanics of solids type of course. So we will use this as a basic review, and then we will move on to something a little more powerful, which is the use of singularity functions, or sometimes also called Macaulay's method. So the basic theory behind the double integration method is the basic Euler-Bernoulli beam equation, which gives the moment and curvature relation, right? Where phi is the curvature and m is the moment, and ei is the bending rigidity. So this is the basic Euler-Bernoulli equation. And u here, u of x is the deflection curve or the elastic curve, which we usually compute using this equation. So just as a quick example, if we consider a cantilevered beam of length L and bending rigidity EI, right? So for this, we can compute the support reactions, let's say at point A, and then we can consider that this is our origin, and from here x starts. So at an arbitrary section at a distance x from the support A, we can draw its free body diagram, and using the support reactions and support moment, we can write an expression for m as a function of x. So this is how the moment will vary as a function of x if the origin is at A and x goes from left to right, right? Now, once we have written the moment equation or the variation of the moment, then we can use the Euler-Bernoulli equation and say that the EI times the curvature is equal to the moment. And this equation we integrate 2 times. So after first integration, we get the slope, and after the second integration, we get the deflection. But of course, this integrating 2 times introduces 2 constants of integration, C1 and C2. And in order to determine C1 and C2, we use the boundary conditions, right? So for example, in this case, the boundary conditions will be that slope at x equal to 0 or will be 0, and the deflection at x equal to 0 will be 0. So using these 2 boundary conditions, we obtain the 2 constants of integration. Both come out to be 0 in this case, and subsequently we can substitute these constants, C1 and C2, we can substitute this back to the elastic curve equation, u of x, and we can write u of x as a function of x in this way, right? And then let's say if we have to compute the tip deflection, we can evaluate this function at x equal to L, and that basically gives us the deflection. So basically we can evaluate this function of u of x at any x, and that will give us the deflection at that point. Similarly, we can evaluate this function u prime of x at any x, and that will give us the slope of the beam at any particular point. Now, you would have also seen an alternative approach where the same beam theory says that the fourth derivative of u times the bending rigidity gives the load intensity, right? So this there was a UDL of minus q acting on the beam, so this is the load intensity. Now in this case, we are at the fourth derivative of u, so we integrate it 4 times, and subsequently we get 4 constants of integration, 1 at each step, so C1, C2, C3 and C4. And now we need to use 4 end conditions. So basically first 2 are on deflection and slope, which is that deflection and slope at the left end are 0, and the second 2 conditions come from the moment and shear force at the right end equal to 0. So at the free end of a cantilever, the moment and the slope will be 0, so that is what gives us the other 2 conditions. And basically then we can again find out C1, C2, C3 and C4 and substitute it back to the elastic curve equation, and we would find that this comes out to be same as earlier, which is expected. We may look at one more case very quickly, that let's say if this cantilever beam is subjected to a tip load of P. Again, we can draw the free body diagram of the portion at a distance x from the support A, right? And we can write moment as a function of x. In this case, it comes out to px minus pl. So again, we will write the Euler-Bernoulli beam equation, and then from here we can integrate it 2 times. There will be 2 constants of integrations, and from the boundary conditions again applied at the end A will give both of the constants come out to be 0, and eventually we can write u as a function of x. We may also write theta as a function of x, or u prime as a function of x. And again, if you evaluate the tip deflection in this case, it comes out to be minus 3pl cube by minus pl cube by 3ei. This is something that which many of you might also have remembered. Let's look at one more example. Now from here we will begin a little bit of motivation towards the Macaulay's method. So let's say there is a simply supported beam, and the load is being applied at L by 2. So at mid-span of the beam. So this is L by 2. So in this case, the bending moment diagram, or the BMD, you know that it comes out to be of this shape, a triangular shape. But if we intend to write a moment as a function of x, it takes a different form in this half and a different form in this half. So the equations are different, right? So m of x, we are writing that it is equal to px by 2 for the span AC, which is between 0 and L by 2, and it takes a form of this kind in the span CB, which is between L by 2 to L. Okay, so if we consider these spans AC and CB, now the Euler-Bernoulli equation on the right hand side, the moment will be different for both, right? So basically now we need to integrate 2 times, but separately for AC and for CB. So the u which we are calculating for AC can be only used to calculate the deflection in the AC portion, and the CB can be only used to calculate deflection in the CB portion. And now actually we get 4 constants of integration. So C1 AC and C2 AC from here, and C1 CB and C2 CB from the CB span. So we have basically 4 constants of integration, but we still have only 2 boundary conditions. One is that uac at 0 equal to 0. So remember that we cannot call this u of 0 equal to 0 anymore, because u in the AC span and u in the CB span will have different functional forms. So we are saying that uac of 0 equal to 0 and ucb of L equal to 0, which is basically, since this is a simply supported beam, deflections at both the ends is equal to 0. But now we will need 2 additional conditions which will come from geometric compatibility. So what we are saying is that the deflection should be continuous at C, which is the midpoint, and the slope also should be continuous at C. So we are saying that uac of L by 2 should be equal to ucb of L by 2, and u dash AC of L by 2 should be equal to u dash CB of L by 2. So this will give us the 4 equations. We may obtain the constants, and then when we can write uac and ucb. So I mean, the challenge here is that we have different expressions for different portions of the beam, and you can imagine that if there is a beam with multiple concentrated loads, right? So if there is a beam with multiple concentrated loads, and maybe a concentrated moment here, or a UDL in some portion. So in this case, for each particular span, we will have to write a different equation of m of x, and consequently we will get a different equation for the deflection. And whatever is this number of spans, we will have to generate that many additional compatibility equations. So the number of integration constants will also be a large number, okay, if the number of forces being applied is large. So one way to circumvent this problem is the use of singularity functions. And with that, we will move on to the Macaulay's method. So basically, this is a step function type of thing, where the basic mathematical definition is like this: that if f of x is equal to this angular bracket x minus a to the power of n. So this angular bracket is a special notation which we are introducing. Um, so this is defined as x minus a to the power of n, a polynomial, if x is greater than a, and this is defined to be 0 if x is less or equal to a. Okay, so if you look at a few examples just to get a sense of what this is, if we say angular bracket x, or in other words, angular bracket x minus 0, so for x less than or equal to 0, this remains 0, and for x greater than 0, this is x. Okay, so this is the line which represents x. Similarly, if you look at angular bracket x minus 2 squared, so up to x less than or equal to 2, this will remain 0, and after that this will behave as x minus 2 whole squared. Okay. Similarly, we can talk about angular bracket x minus 1 to the power of 0. So for x less or equal to 1, it remains 0, and for x greater than 1, it takes a value 1 because the exponent here is 0. So the value becomes 1, right? Yeah, so this is how these angular brackets span out. Now, you may argue whether this equality should be in the less than equal to portion or in greater than equal to portion. But if you really see that at x equal to a, the function comes out to 0 from both sides. So this equality you can take anywhere. So basically, this is a continuous function. Okay. And another property that we ascribe to them is that they integrate like polynomials. Okay, but they carry this angular bracket throughout. So for example, if you have to do integral of angular bracket x minus 9 dx, this will be just angular bracket x minus 9 whole squared by 2 dx. So this is like integrating, let's say if you were integrating a polynomial x minus 9 dx, this would have been just x minus 9 whole squared by 2 plus the constant of integration, right? So now here we are just carrying these angular brackets as it is. So similarly here, if you are integrating angular bracket x squared, we are saying this is x angular bracket x cubed divided by 3 plus c. And if we are saying, let's say, angular bracket x minus 4 to the power of 0 dx, this is angular bracket x minus 4 to the power of 1 plus c, right, and so on and so forth. Now it is important to carry this angular bracket as it is, because that will play a key role in computing the constants and calculating deflections or slopes at a point. We will see how that comes later. Okay, so with this background and motivation, let's move to the Macaulay's method. So the biggest advantage of Macaulay's method is that it allows writing of the expressions for m of x and consequently for the slope and deflection as a single expression for any beam for any loading case. So if you recall that earlier when we were using the double integration directly, we had to write different expressions for m in different spans, but this method will allow us to write the same expression which will be valid for all the spans. Okay. Now before we move on to the examples, let's just see a few quick things. So let's say if this is a span where the type of load being applied is a concentrated load or a concentrated point load, right? Now let's say this is some reference point from where we are counting x, and the load is acting at a distance a from this reference point, and we are calculating the bending moment at a distance x from the reference point, and this make sure that this you are following the sign convention, right? So in this case, m will be equal to minus p times x minus a angular bracket to the power of 1, right? So what it means is that if x is less than a, which means if we are talking about anywhere here, cutting a section anywhere here, then this moment due to P will be 0, right? And that is what this angular bracket will do. So what we are seeing here is this is minus P times x minus a for x greater than a, but it is 0 for x less than equal to a. So if x takes a value, any value less than a, which is in this span, the moment due to P will remain 0. But if x takes a values anywhere here after P, then it will take a value of minus P times x minus a, which is what it should be, right? Similarly, if we look at a case where there is a UDL of intensity Q, which starts from a distance a but then continues throughout the rest of the length, right? So if we try to write m of x for this, it will be now minus q times angular bracket x minus a whole squared by 2. And again, if you reason in a way similar to what we did earlier, and everything is starting from this reference point. So for the span where x is less than a, this moment should be 0 due to q. But if we take any section here, where x is greater than a, the moment should be minus q times x minus 2 whole squared by 2. And that's what this angular bracket expression allows us to write. So similarly, we can look at one more case where, let's say, there is a concentrated moment applied at a location A, again from some reference point. Now the bending moment induced due to this applied moment will be minus m bar times angular bracket x minus a to the power of 0, right? So if we are anywhere here, which is x less than equal to a, m of x should be 0. So for x less than a, this will give us 0. But if we are anywhere here, which is x greater than a, the bending moment should be simply minus of m bar. And so if you see, this will become minus of m bar times x minus a to the power of 0, which is minus of m bar. Okay. So this angular bracket notation allows a neat representation of the bending moment along the length. And one thing to remember would be that if we are talking about a concentrated moment, right, then the power will be 0. If we are talking about a concentrated load, the power will be 1. And if we are talking about a UDL, the power will be 2. And you can continue to reason that way, and you can write generalized expressions for, let's say, if there is a linear load, sort of a triangular load, or if there is a parabolic load, these exponents you can exponents and the denominator you can generate. Okay, let's look at an example. Let's in fact relook at the previous example where there was a concentrated load applied at the mid span of a beam, of a simply supported beam. So here if we see, there will be two support reactions at p by 2 at both ends, and there is a concentrated load. So in effect, there are three concentrated loads acting on the free body of the beam. Okay. So now we can begin to, we will say that, this is our reference point. So one important thing is that the reference point should not change throughout the beam, right? So once we say that A is the reference point, we will retain A as the reference point throughout, and X will always start from A. If we cut at this point, right, which is between X between 0 to L by 2, we have a situation where there is a p by 2 load acting here. We want to calculate m of x here, and this is x, right? So this is a load which is acting at x equal to 0, and this is a concentrated load. So we will have the m will be equal to p by 2 times angular bracket x times x minus 0 to the power of 1, right? So this is what we have here. Now the second span, when we go here, So there will be this expression will be also there, but now we will get one more expression due to this applied load P. And since this applied load P is acting at L by 2, right, and our x is this, so we will have P times angular bracket x minus L by 2 to the power of 1, right. So the power of 1 is there because this is a concentrated load. And finally, although this is redundant, not necessary, but there is a load being applied at x equal to L, so we may also write that the moment due to that is P by 2 times x minus L to the power of 1, although this term will be always 0 because the maximum value of x is L, and in that case this angular bracket will become 0, so x will be less or equal to L, so this will become 0, right. So and another thing to note here is that this angular bracket x minus 0, since here you have 0, so and x, the minimum value of x is also 0, so that simply becomes a simple polynomial, so P by 2 times x, and then we have minus. Now this the second term we will have to carry the angular bracket, so this is minus P times angular brackets x minus L by 2. Now we integrate once, so we get px squared by 4, this is this term, and the second term we will carry like this, so we integrate it, so we get a 1 by 2, and then this angular bracket gets raised to the power of 2, and then there is a constant of integration. Okay, now we integrate once more, so this becomes px cubed by 12 minus we get a 1 by 3, so that becomes P by 6 times this angular bracket raised to the power of 3 plus C1x plus C2. So now this for both the spans we are able to integrate simultaneously, and then we can apply the boundary condition. So first one is that u at 0 is equal to 0, right. So basically in this equation we will put 0, so this becomes 0. Here if we put x equal to 0, 0 is less than L by 2, so this becomes 0, and here it is 0, so from here we get C2 is equal to 0, right. And the second equation boundary condition is u at L equal to 0. So now here here we get PL cubed by 12 minus P by 6. Now here we put x equal to L, right, so x equal to L. So now this L is greater than L by 2, or x is greater than L by 2, so this will actually become a simple bracket or a simple polynomial, right. And then this C1 times L, all of that equal to 0. So from here we can calculate that C1 comes out to minus PL squared by 16. Okay, and now we can substitute back the constant into the elastic curve equation, and we can write u of x as a function of x, and notice that now we are able to write a single expression for the entire beam, and we are carrying this angular bracket within that, right. So if we have to calculate, let's say, deflection at the midpoint, we have to evaluate this at x equal to L by 2, right. So this first term is simply L cubed by 96. Now the second term at x equal to L by 2 will be 0, and then the last term gets this, so eventually we get the midspan deflection to be like this, right. So this allows us to do very straightforward and single expression manipulations for the entire beam. Let's look at a little more complicated example. So let's say this is a simply supported beam of span 10 meters. There is a concentrated moment applied at 2 meters, and then there is a partial UDL on this span which starts at 4 meters and ends at 7 meters. Okay, and if you recall, the expression for moment for a UDL case was there for a situation where when it starts at a particular point but then it continues throughout. Now one way to handle that is that we extend this load to the rest of the beam, but to compensate and to ensure that the forces remain the same, we apply an equal and upward force UDL in the span where there was no UDL. So here there was no UDL, so we extend this 10, but we also apply the 10 from the bottom. Okay. And once we have done this, we can calculate the support reactions, and then we can write the expression for moment directly. So if you see, so m of x becomes 11.5 times x. So again, the reference point is here, and x is starting from here. So this 11.5 times x plus 20. Now 20 is a concentrated moment. So we will have angular bracket x minus 2. So x equal to 2 is the location of this 20 kilonewton meter moment. And since it is a concentrated moment, the power becomes 0. Then we have 10 by 2 times angular bracket x minus 4 to the power of 2. So this is basically 4 meters. So A is equal to 4 in this case, right? And then we have the force we have applied to make sure that the effect of this force is nullified after 7 meters. So then from this red upward force we have plus 10 by 2 times x minus 7 squared. Okay. And in case of any confusion, you can look at these individual free body diagrams where different cases for x are being considered. So x less than 2, and then x between 2 and 4, and so on and so forth. So once you've written that expression for moment, then we can write the elastic curve equation, we can write the Euler-Bernoulli beam equation, where EIU double prime becomes this. So we integrate once, so this term comes like this. This term becomes 20 times. Now this power 0 becomes power 1 after integration. This term comes here, and this term comes here, and then we get one constant of integration. We integrate once more. This term is like that. Now, so see this. These are just integrating like polynomials, right? This comes here. This comes here. This comes here, and then we have one more constant of integration. Next, we can apply the boundary conditions. Okay. And you can try to reason why certain numbers are of the form like they are by using the properties of the angular brackets. Okay, so from here we get C2 equal to 0, C1 comes out like this, and then basically we can write expressions for the deflection as well as the slope, retaining all the angular brackets as they are. So this is the only important thing here, that we need to retain all the angular brackets wherever they are. And the other important thing is that the reference point needs to remain the same. So from wherever we start counting x, that reference point remains the same, right? And once we have these expressions, then we can basically calculate anything that we want. So we can calculate slope at specific locations. So for example, here the slope is calculated at the two ends. We can calculate deflection at any point. So let's say if you want deflection at 5 meters, we can calculate that. And as long as we are respecting the properties of the angular brackets, we will be fine. So for example, if we calculate u at 5, we will have 1.92 times 5 cubed plus 10 times, now this 5 is greater than 2 here, right? So this will be into 3 squared. So 5 minus 2 is 3. Then we have minus 0.42 times 5 minus 4, right? So that is still positive. So 5 is greater than 4. So we will have 1 to the power of 4 plus 0.42 times, now here 5 is less than 7, so this becomes 0, and minus 204.97 times 5. So whatever number this comes out, that will be the deflection at 5 meters. So in this way, we are able to leverage the angular bracket notation to facilitate the process that we are able to write the same expression of moment throughout the span of the beam. And we need not carry out different integrations. We can integrate all of that together, and then we can, we need to carry these angular brackets as they are, and then we can calculate slopes and deflection at any point, anywhere in the beam.